Welcome to EDU World Space.
For this question, we are trying to find the expression for the minimum kinetic energy that is required, right, for the case when we have a mass m1 that is firing towards a stationary mass m2 to produce the final products m3. Right, m3 consists of all the masses of the final products, and the minimum amount of kinetic energy required for m1 for this entire reaction to occur would be the case, right, when the final products all have minimum amounts of kinetic energy, and this would imply that they must all be moving together, right, at the same velocity, so that the total kinetic energy is a minimum at the end. So at this condition, we want to find what is the kinetic energy of our initial m1. And to start off, we're going to use conservation of energy. So conservation of energy tells us that the total initial energy would just be the kinetic energy of m1 plus the rest energy of m1, kinetic energy plus rest energy of m1 plus rest energy of m2, because m2 is at rest. So that's all the initial kinetic energy. This is equal to the final energy of the total masses of our products, and this is from the rest energy relationship. This is from the energy momentum relationship, right, where E square is equals to P square C square plus M square C4. So if you take the square roots, we get the energy. Right, so from here, what is our P square C square? Right, we don't know what is this, but what we can do is to relate this P square C square to the initial momentum of the system, right? So the P square over here is the final momentum of the system. By energy conservation, this must also be the initial momentum of the system, and the initial momentum only comes from mass m1, right? This is the only contributor of the initial momentum, and this momentum expression can actually be derived from the energy momentum relationship of our mass m1, right, where its total energy of m1 is equals to P square C square plus M square C4. Right, so this is energy momentum relationship again for m1, and this P is the same P as this P, right, by conservation of momentum. So what we can do is to replace this P square C square with E1 square minus M1 C4. Now after doing this substitution, we need to then substitute what is E1, right? So E1 by conservation of energy is just the kinetic energy plus the rest energy. Very simple. We can then try to substitute this in, and then simplifying this equation, right? This plus this is equals to this, and we can simplify that by squaring both sides. So we're going to square both sides to get rid of the square root. So for the left hand side, squaring the left hand side first, this square, this is the expression that we will get, right? We expand it out, and then squaring the right hand side, we just get rid of the square root. So nothing much except for substituting in what is E1 squared, right? So E1 squared will be this expression here squared, and we just substitute that in, which is this expression here. So right now we have these two expressions which have a lot of common factors. So the common factors include this K2 times Kmn, Kmean times the M1C square. So this over here can cancel it out. Then we have M1 square C4 minus plus, so that's gone. Then we have K minimum square, which is appears here as well, both sides. And then for the rest of the terms, we're going to try to simplify. Right? I'm going to keep this k minimum times m2c square on the left hand side while bringing all the other terms to the right hand side. So this term all the way to the right hand side, and this is the expression that we will get. So from here, very simple, very easy to find our k minimum, what we want. We just have to rearrange the equation, right? So this over here becomes m1 plus m2 square, because we have m1 square plus m2 square plus m1 m2, right? So sorry, this is 2 m1 m2, right? I'm missing a 2 over here. Should be 2 m1 m2, right? Over here is 2 m1 m2. So we can put them together into a square, and then factorize out the c4, and we divide the 2 m2 c square over as the denominator, and then we can then simplify this into this final expression, which is what the question wanted. Now for the second part of this question, basically what we are doing is to put in some values, right, actual values, to determine what is the threshold kinetic energies. Right? So we have 3 different equations that we are interested in. For the first equation, it's just P plus P plus 3 protons and 1 antiproton. So M1 over here is the mass of the proton. M3 is mass of 4 protons. So we're going to use the masses in terms of MeV per C. Alright, so it's 938.3. MeV per C. So we have M1 plus M2 because they are both the same masses, so we just multiply this by 2 square. Sorry, I have to deal with M3 first. So M3 is just 4 protons square minus 938.3 times 2 square. Multiply this by C square divided by 2 times of M2, where M2 is mass 938. So the answer that we should get would be about 5630 MeV. So this is the kinetic energy that will be required. Sorry, this is MeV per C square. The units. Now for the second equation, we're looking at pion being the M1, right? The proton is at rest, fire towards the kaon to produce the kaon and the lambda naught baryon. So I'm gonna start off with the pion. Pion mass is about 139.6. Proton 938. It's the mass of the kaon. And then for the lambda, it's sorry, this is 1115.7. MeV per c square. So we have M1 to be this. This is our M2. This is our M3. So the minimum kinetic energy is the previous equation, M3 square is 493.7 plus 1115.7 square minus M1 plus M2 square multiplied by c square divided by 2 times of M2. And we should get 761 MeV. For the third equation, we have two protons producing two protons and one neutral pion. So the pion mass is 139.6 still. Mass of the proton is 938.3. So the minimum kinetic energy, M3, be just taking 2 times of 938.3 plus the mass of the pion minus m1 plus m2, which is 2 times 938.3 square. I think by multiplied by c square divided by 2 times of the mass of m2. And for this, the answer is about 290 MeV. For the final equation, we have one proton and one antiproton producing the Z0 particle. So this Z0 is given as 91.2 GV per c square, which is also 91.2 times 10 to the power 3 MeV per c square. Right, to keep the units all in terms of MeV, then can find the minimum energy. Take m3.2 square minus m1 plus m2, which is 938.3 times 2 square, holding multiplied by c square divided by 2 times of m2. And for this answer, we get quite a large value. This is around 4.43 times 10 to the power 6 MeV. Which is equals to 4.43 tera electron volts.